It's time for some more Smarter Every Day. Specifically, how to think about radiation and entering a nuclear plant. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
I'm about to show you a video of the moment when two nuclear plant workers tell me how they really feel about the safety of their job.
Well, I guess I'll be number 3.
I wish the whole public knew how safe what we really did was, considering how dangerous what we're dealing with is.
Okay, so I see the TVA logo on that screen. That's Tennessee Valley Authority. And this says BFN, so Browns Ferry Nuclear Plant in Alabama is where he's at. All right.
Do you agree with that?
Yeah, absolutely.
I think nuclear power would be tenfold what it is today if we had done a much better job of educating the public.
Preaching to the choir there, buddy. I can only imagine where would we have been now if we would have done a better job at that when nuclear power first became a thing.
A lot of people come to me and ask me, what is nuclear dangerous? I'm like, the people that I know, they retire out, they die of other natural causes, not related. It's not cancer. We don't have all these issues. You'll hear a lot of propaganda.
No, I've never heard of anyone getting any sort of illness related to working at a nuclear power plant. And as far as workplace safety is concerned, nuclear power plants have among some of the highest safety records, according to OSHA, of any comparable sized industrial facility.
Not of nuclear, but it's just one of the safest things that we ever do.
Because for the most part, it's a very low amount of dose. Occupational dose is exceptionally low, right? So
yeah.
So I go in radiological controlled areas, and while doing and your dose gets measured when you enter, counted when you leave. Gone in and out and gotten 0 dose even when going into radiological controlled areas. Now, there are some jobs that occasionally get a little bit, but it's all very safe, very controlled, very clearly briefed, and yeah, it's just the safest there is.
I mean, for example, we're talking operating the millirem over here, like a chest x-ray's 10 millirem, maybe.
Millirem's a very small unit. The dosimeters I used were going down to the tenths or hundredths of millirems, and we're not talking very much. To give you a sense of scale, the dose limit for a radiation worker is 5,000 millirems per year. The amount at which a risk of cancer is evident is 10,000 millirems per year, or 100,000 microsieverts, depending on what unit you're familiar with. But 1 sievert is 100 rem.
A single x-ray?
Single chest x-ray is like 10 millirem.
Got it.
And I won't see that
Yep, that's about right. Chest x-ray is typically about 10 millirem.
a year, maybe, depending on what you do. Some people will see more than that, but definitely not within one trip in the plant.
Right.
This is the second video in the Smarter Everyday deep dive series into nuclear power. I've always kind of instinctively thought nuclear power was a good idea, but now I'm trying to understand it at its core.
Happy to help you there, buddy.
And to do that, we're traveling all over the country and meeting the people that know this stuff, and I'm asking them the hard questions. I'm so excited about this whole series, and today's video is about radiation and how nuclear workers stay safe. Nuclear is a loaded word. It has an association.
It's a shame it is, because, yeah, people immediately think of weapons first.
With nuclear weapons, which is understandably scary. And there's other words like contamination and radiation. If you don't understand what's going on around the
Those two things are different, by the way. A lot of people get contamination and radiation mixed up.
physics involved in these words, it can be quite frightening. Those two men that I just showed you in the video, they work around nuclear reactions every day, and they've done it for decades. And they're not afraid.
Technically, everybody works around nuclear reactions every day, but let's see what you mean. But I see what you mean. Fission reactions in a power plant, sure.
It's clear to me that they have some kind of understanding I don't have. And I'm guessing you might not have that understanding either.
I will gladly fill in some gaps, if there are any. I mean, I don't know what these guys' jobs are at the nuclear plant, but every nuclear plant employee, you receive at least some general training. So you don't have to be a nuclear engineer to work at a nuclear power plant, but you will be trained on how to work safely in a radiological environment. And even if you're not cleared to work in a radiological environment, you're going to still receive some high-level training about radiation and nuclear safety.
You're about to receive training to enter an active nuclear power plant. At the end of this video, you and I are going to enter this nuclear...
Okay, so he's just by showing these pictures, man, this takes me back to my initial employee training. So it looks like security doors, protective clothing, radiation protection. At the plant I worked at, they were simply called General Employee Training 1, and that was mainly about plant access and what's located at the plant, and General Employee Training 2, which is about radiation protection.
Power plant into a special area of the plant.
Yep. Recognize, wow, this is, I've never worked at Browns Ferry specifically, but a lot of this stuff is pretty well standardized, at least within the U.S., whichever site you're going to be working at.
It has both contamination and radiation. And the hope is that when we're armed with this new understanding, we're going to be...
You can have radiation without contamination, and you can have contamination without radiation. And you can have radiation with contamination.
Just as confident as these gentlemen are. Let's go get smarter every day and learn more about nuclear power.
It's a fun animation.
In the first video, we went out to Idaho National Lab, where we saw EBR-1, the world's first nuclear...
If you haven't seen my reaction to that one, I'll put it in a comment down below.
Your power plant. That particular plant was a fast reactor plant that also bred new fuel. That video laid the foundation for our understanding on how neutrons drive nuclear reactions. This was cute,
his little mouse traps.
This is the second video in this series, and today we're going to do something really cool. We're going to go to Browns Ferry Nuclear Power Plant here in North Alabama.
Yeah, I could kind of see that on their little presentation paperwork. Yeah, if you've worked at one nuclear plant, at least within the U.S., you can kind of tell just at a glance where the other plants are. It's a fairly tightly knit community. It's possible I'll see some people I recognize.
This plant is a really, really big deal for my local area. It's operated by TVA, the Tennessee...
And this is a sizable station. It has 3 units. And all 3 combined, I believe, produce just under 4,000 megawatts on the grid. So about 12,000 megawatts total in terms of heat.
Valley Authority, and it contributes power to the grid for houses all over North Alabama and the surrounding area. So after a long process to get permission to enter the plant, I got a phone call that said, hey, you need to come out and do some training first. I usually shoot Smarter Everyday videos along...
That's absolutely true. Oh, and here's the deal. You go through training even if you've... I would go through the same sort of training if I was invited to Browns Ferry, even though I already have extensive nuclear power plant experience, because there are a few things that are unique to each site. Now, it's not quite like starting over, and it kind of depends on the nature of your trip, what you'd get training on, especially if it's a person from one site visiting another site, but there is always lots and lots of training in nuclear power plants.
Just me and a camera. But every once in a while, when something's very challenging, I ask my buddy George, who helps me make these videos, to tag along with me, and that's what we did today. We went out to Browns Ferry for the training, and George and I were talking about it. We were expecting maybe an hour, something simple.
Okay, here we are, Browns Ferry Nuclear Power Plant. We got
Yep, they usually have their own training buildings that are outside of the power block, or outside of the protected area, depending on where you were.
Trained on how to go into a nuclear plant. This will be cool.
This is Bill Ball. Bill was introduced to nuclear power at the plant where his dad worked. He then went into the Navy with nuclear submarines, and now he runs a team at Browns Ferry that's in charge of making sure the plant is operational.
Fairly common to hire people outside of the nuclear Navy. I was not one of them, but I would say round about half the people I worked with were, especially within the operations division.
This is my longtime buddy, Philip. We've known each other forever. He's been in my phone for over a decade simply as Neutron because he works at the nuclear plant and have always wanted to see what he does.
What are we doing today?
Well, today we got to get you set up for rad worker training, essentially is what it boils down to. We got to test you. We're going to train you and test you a bunch so we can get you...
Yep, you have to pass a test. There's going to be a computer-based or written-based test on... Do you know about the radiation hazards? And there's going to be practicals about how to don and doff protective clothing.
Dosimetry, so we can get you in the plane to see what you want to see.
Okay, so I've got to get one of these on, like a dosimeter.
Yes, sir.
Okay.
Yes, sir.
Okay, cool. Sounds good.
One interesting thing is if you're coming from another plant, they take into account your total dose accumulated over your previous plant. So they take into account how much dose you've had at previous plants before coming here, or at any other plant.
And you're going to do it?
I'll be around.
So is Philip going to be my escort? Is that how we're going to do it?
I'm your escort right now. Philip's going to help too. So us two will be getting you around the plant or around the training center.
Okay.
Escorts got to have positive control on you at all times. They don't follow you into your own bathroom stall. It's not that crazy, but it's close.
Okay, sounds great.
These are badges. These are for you.
Thank you.
So get you in and out of here.
Escort required.
I just need those back when we're done for the day, please.
Bill really spearheaded getting us into the plant. They both work in the instrumentation department at the plant, and you'll get to know them a lot more as we go. We made our way down to a classroom.
So instrumentations and controls.
Where we were introduced to a guy named Roger who was in charge of our training.
Give you all some CBT training today.
Yep.
For your dress out, before it's the prerequisite for your dress out.
Saw that
It's going to talk about the radiation worker process, checking in and all that stuff, and explain kind of the nuclear fission process and things like that to you, okay? Sure.
Okay, sounds good.
You guys pick a computer out here.
Sweet.
I wonder if they're going to be allowed to show some of this, because some of this is proprietary.
Are we actually gonna dress out today?
No, probably won't get to that today because this training here will take between 4 to 6 hours.
Okay.
Yep. First week on the job, you're basically in a computer lab doing training. Because at that point, or you could do it at your desk, but since I was brand new, I didn't have a desk yet.
So we'll get that done today and then have your dress out class scheduled for in the morning, first thing.
I've had the opportunity to visit some very incredible places, and usually once you meet the security criteria and a certain person signs your badge or whatever, you can go in. It's not a big deal. This was very, very different.
That it is.
Because I had to take training, and it wasn't...
Nuclear power is special and unique. I wonder if... I'm pretty sure he's going to be told that several times. Whether or not he'll show that in his video is, up to him, but that's the phrase that I've heard from just about anyone working at any nuclear power plant in the U.S. is the phrase special and unique. And that's due to the robust amount of safety systems.
Just like, sit down and let us talk to you for a few minutes. We're talking hours and hours and hours of computer-based training.
Okay, he's blurring it out, but yes.
We had to go through in order to
Yep. Nope, I can kind of tell what's on it, though. Just yellow and magenta radiation area type signs.
Get access to this place, and they gave us an exam. We had to take an exam to make sure we could do it. This was
got to make 80% to pass, and if you don't, well, you have to take it again.
Far more intense than I expected. This was just day one of training. So I didn't understand what I was getting into at all. And that fascinated me. It made me realize this is a different thing than anything I've ever done. I learned so.
And it's going to be more strict here than it is in his previous video where he went to a lab. Because commercial nuclear power, there's way more strict rules than people playing with reactors and doing experiments. I've done that before too. It's a lot of fun, but anyway.
So much in this training. We even looked at the core of the reactor and how that works. And there's one thing that stuck out with me in particular that helped me understand radiation itself and all the different ways radiation happens. So I want to show you this, and we're going to run through.
The most dangerous form of radiation is visible light because you can see things that can be misinformation. I'm kidding, but not really.
It, and then I'm going to show you it again one more time, okay? So, nuclear fission. We talked about this in the first episode.
Did you actually put 235 on there?
Uranium-235 splits into multiple atoms, and when it does that, there's this release of a tremendous amount of energy, right? But
200 million electron volts per fission. To give you a sense of scale, chemical bonds released from, say, burning coal are in the 2-3 electron volt range. So yeah, way more energy dense.
we didn't really talk about the radiation that's released as well, but that's also a thing. So we have this event and we have these daughter products of uranium-235 splitting, but we also have radiation. And what they do in a nuclear plant is they control the areas where this radiation happens, and it's called the radiologically controlled area, the RCA. In the RCA, there's multiple types of radiation.
I actually really like the term radiological controlled area because every area there's radiation. I mean, there's different types of radiation. You can get radiation from the sun. You can get radiation from rocks, uranium ore. There's radon gas in mines. But radiological controlled area, that is where you put engineering controls in place, like dosimetry you have to log in, physical barriers, signage, so everything is carefully controlled and monitored. You have to have a briefing with radiation protection before you go in. But technically there could be radiation anywhere. But this is just where you're controlling, where you're monitoring it within a nuclear power plant, or within a lab, or high energy physics such as a particle accelerator.
Radiation that can affect biological life and cells in your body, and they control them in different ways. Let's talk about the 4 types of radiation. The first one I want to talk about is
so specifically, these are the 4 types that you're commonly trained on at a nuclear plant, and specifically types of ionizing radiation. So things like, my earlier comment about visible light, that's not included in these 4 types.
Called alpha. Alpha radiation happens when the components off these atoms fly off, and you get something that looks like the nucleus of a helium atom, right?
It is the nucleus of a helium atom.
2 protons, 2 neutrons, so it's really big. Got a little excited with the...
That one's a little big there, buddy. Looks like you got some helium-5 there. And so that's not it. And the reason is because helium-5 is less stable than helium-4. Helium-4 is your stable one. So things that decay using the alpha mode of decay, a helium nucleus is a nice stable amount that it sloughs off when the radioisotope tries to go to a more stable state. That's why radioisotopes decay to begin with.
Model, there's an extra neutron, pretend that's not there. And it can fly off, but it
can be in a very enthusiastic amount. You could argue that's spontaneous fission, because spontaneous fission is when something sloughs off something bigger than an alpha particle. That's pretty rare, though, and you're not really going to see that very often in a nuclear power plant. That shows up in a bunch of weird high-energy physics experiments.
Easy to stop. It can be stopped by something.
That's spontaneous fission, not to be confused with fission that you're doing on purpose.
As simple as paper. So if this alpha radiation comes in contact with paper, it stops, which is cool because this means...
For the most part, I mean, anything with radiation interaction with matter is a massive probability function, but yeah, paper will stop most of your alphas. However, do not eat the alpha sources because then you're going to get a very high internal dose. In fact, the dose you're going to get per alpha compared to per gamma is 20 times higher, provided it actually goes inside you. So alpha is a very different type of hazard that you engineer for compared to, say, gamma radiation, but I think I'm getting a little bit ahead of it.
We can use anything thicker than paper to shield against alpha particles in our radiologically controlled area. The second type of radiation is called beta radiation. Now, beta decay usually is like an electron or even a positron, okay? So
most commonly an electron, but it can be a positron, so that's right.
These electrons fly off, but they can fly right through paper. They go all the way, but plastic can stop them, right? So you can't stop beta with paper. You can stop it with plastic, though, which is why I think this is very interesting. You'll see people in nuclear plants wearing safety glasses, and it's not that...
That's not... Actually, I mean, it's just because you're in an open plant environment. The bigger hazard isn't beta radiation, unless you're going into an area that you're specifically briefed for that. It's just going to be dust, falling hazards, cutting hazards, anything that just makes dust that can get in your eyes. That's probably the bigger threat to you than beta sources at a nuclear power plant, unless you're going in a specifically briefed area. But yeah, plastic, they are thick enough, even credit cards are thick enough to stop your typical low energy betas. In order for betas to penetrate that, you'd have to accelerate them, which we don't do on purpose at a nuclear power plant. Just like I said with alphas, it's all a probability function. Some of them's going to get through, but it stops most. And that's really what you care about, stopping most.
They're trying to protect from, cutting things with a saw or anything like that. They're literally wearing safety glasses.
But there are tasks that do involve cutting things with a saw or things like that. So want to be careful with that, because it really depends where you're going in the plant and what you covered in the safety briefing or the radiological briefing. So I'm just going to say it depends on where you're headed in the plant and what job you're going to be performing or overseeing.
Is because this plastic, this polycarbonate right here, can stop beta radiation.
Your clothes can also stop beta radiation. Your credit card can stop some beta radiation. Your skin can stop a lot of alpha radiation.
It's very interesting. Beta is bad to get in your body. You don't want to ingest it. You don't want it in your eyes, things like...
True. Alpha's even worse, though.
Like that. So beta is something that you can stop with something as simple as plastic. The third type of radiation that I want to look at, I think is probably the most interesting to me, and that's gamma radiation. Gamma radiation is not a particle. It's a wave, a very high frequency wave.
That's your $1 million question right there. It's high energy light, and is light a wave or a particle? Yes. So make of that with you will. It's a photon if you want to call it a particle, but it's also a wave if you want to call it a wave. Very high energy.
Higher frequency even than X-rays. It can go through paper.
Higher frequency, higher energy, they go hand in hand. See the equation, E equals H times nu, so sure.
Like it's nothing. They can go through plastic, all the way through plastic. It goes all the way, and you're typically going to want to stop gamma with something like lead.
You're going to want it thicker than that too, depending on how much you want to stop it, but usually 8 inches ought to do it.
Now when you go to the dentist and they put this lead apron on you to stop the X-rays, well, gamma is higher frequency than X-rays, and it can penetrate.
That's overkill, by the way, because dental X-rays, you get very little dose. Millirems, that's about half a millirem, which is way less than like a regular chest X-ray or a CT scan.
Penetrate things, kind of like X-rays, but even more energetic. So it has to be stopped with something like lead. Okay, so we have alpha, beta, gamma. There's another one that's fascinating, and that is neutron radiation. Do you remember in the first...
Neutrons, there are some classes, not at nuclear plants, but teaches the big three is alpha, beta, and gamma. Neutrons are one of the special nuclear plant ones because neutrons come from fission, and they're mainly a dose when the reactor is operating.
Episode we talked about this little guy, wee little fast neutron. Well, neutron radiation comes off of this event, and they're very, very fast.
You mentioned fast neutrons, so the amount of dose equivalent multiplication factor can be anywhere from 5 to 20. It's higher for those fast neutrons. Those are less common overall, but you're still going to pick up some fast neutrons at Brown's Ferry, for instance, even if the reactor doesn't typically make fissions in the fast neutron spectrum.
They can go through all kinds of stuff. They're going to go past your paper, past your plastic, even lead. They usually have to be stopped by concrete, specifically concrete that has a high water content.
Yeah, hydrogenous material stops them. That's one of many reasons why the reactor containment building is made out of concrete. The other one is just so it can withstand pressure, an entire energy deposition of the reactor vessel and its coolant system during a catastrophic accident.
An interesting thing about neutron radiation is it interacts with hydrogen atoms quite a bit, and that slows it down. And so if we had water, you could slow down neutrons with water. And so...
Yep. That's one of the ways you get fission to work, is neutrons act as a moderator to slow the fast neutrons down so they can cause fissions. It is also good at protecting you from radiation.
The people that work in a radiologically controlled area, they understand all the physics associated with alpha, beta, gamma, and neutron radiation, and they can control the environment by different types of shielding. And I think that's fascinating. So what I want to do real quick is I want to show you, just with one still shot right here, I want to show you where these different types of radiation stop. Because when I took this training, this is the visual that stuck in my mind, okay?
Sure.
So for alpha radiation, it can be stopped by paper. For beta radiation, it's going to be stopped by plastic after it goes through that paper. And for gamma radiation, it can go straight through paper, straight through plastic. It can be stopped by something like lead. For neutron radiation, it interacts with hydrogen.
Gammas, it's going to be things that are super dense. So tungsten would work. It's a lot more expensive, but tungsten's effective at stopping gammas.
Hydrogen atoms, and so it can be slowed down by water, or in the absence of water, it can be stopped by something like concrete. This is how radiation is controlled in what's called the radiologically controlled area. This is how they shield against that kind of stuff. All of this
not a bad illustration.
Radiation.
I mean, it's very similar to what you would get shown in that general employee training,
which is a very different concept from another word that's very similar in my mind, contamination. These two things are different, and Philip has a pretty interesting analogy to explain the difference.
Yeah, the crudest way that was explained to me, but it stuck with me, is if you imagine your dog makes a mess in the yard. It is, if
Really?
you walk up to it, you can smell it. It is affecting you. but you can walk away from it. However, if you were to step in it and then you track it in the house, now it is affecting all over the place. You are contaminated and you're spreading contamination.
Yeah, this definitely takes place in Alabama. I got family in Alabama, so I get it. But yeah, that's basically it. Contamination, you track it with you. Radiation, you don't. So high radiation area with no contamination, you don't need the fancy protective clothing because it's not really doing you any good. It doesn't really protect you against the spread. What it does for you is it prevents you from taking radiation in its known location and moving it to another. But if you're in a high radiation area with no contamination risk, heavy protective clothing isn't doing you any good.
Makes sense.
Okay, trust me on this. I bought a plastic pile of dog poop to demonstrate this, and then I realized
As one does.
this is an important concept, and I want to learn this exactly once and never forget it. So we're going all in. All right, this is my my friend's dog, Duchess. Duchess, come here. Good girl. All right, here we go. Please forgive me for this analogy, but I think this is going to work. I have a very complicated setup here. I have multiple boards, and we're about to learn about contamination versus radiation. Okay, so I have some contamination right here, right? This is contamination.
And he's wearing gloves.
I don't like it. I do not like this at all. Notice how I take this glove off. That's going to be important later.
Yes, it is. So you don't contaminate yourself. You reach your hand inside. That's part of the practical exam for going into radiological controlled areas. You have to know how to do that.
So right now in this room, there is a smell radiating from this dog poop right now. It's awful. I don't like it. I'm a little sad at my life.
I feel like I should say that smells from dog feces do not constitute the definition of ionizing radiation, but I have zero problem with him saying a smell is radiating from it.
Choices. However, there's a smell coming off. How do I know that? Like, how do I know that there's a smell happening that's unpleasant? And the answer
You have a detector, your nose.
is I have a nose. And that nose is a detector that I'm using to detect that smell that's radiating from the dog poop, right? But what about this radiation right here? We have this unstable atom that has some kind of radiation
or a scintillator,
that's coming off of it. It looks like it's gamma. How do we know where that is?
Gammas, you could use both.
I don't have a detector on my body that can tell me that. By the time I can feel it,
your radiation detectors on your body are only calibrated to 400 to 700 nanometers of electromagnetic radiation, being visible light.
It's way too late, okay? So, radiation workers, or I guess nuclear workers is the proper term, have a very special thing called a dosimeter.
Actually, radiation worker is the proper term that I'm familiar with, because you could work at a nuclear power plant and not go anywhere near the radiological controlled area. You could be in the office building outside of it and wouldn't need to receive training or certifications for any of those things.
This is a DAD, a digital alarming dosimeter, in the way that my nose sends a signal to my brain that says, hey, something's
They have different names. I like that one though, a DAD.
bad and it's probably poop. That isn't in my body. But what this does is it makes a noise with a little speaker, and I can hear that. And that tells me, oh, I might be around radiation. So this digital alarming dosimeter,
it alarms if you've exceeded a dose rate or you exceeded a predetermined dose limit, both of which are set during your radiological briefing. That is to say, just because it alarms doesn't mean you're in trouble. When it alarms, if it alarms, I should say, you do what you said you would do in the brief, which usually consists of leaving the area, leaving away from the known sources that you briefed about, and getting with radiation protection.
detects the radiation coming away from those nuclear atoms, whatever that is. Okay, so let's say that I want to do some form of work in a nuclear plant, in a special room, okay? I'm in this room, and I want to go in here and do something. Oh, but there's a problem. I've got a pipe, and there's water flowing in the pipe, but there seems to be some type of like radioactive particles that have collected in the bottom of this valve. Do you see that? Okay, well, that's probably not a great place to go in.
And this sort of thing could happen. Corrosion products that become activated, if this is a primary system, Activated meaning the neutrons interact with the corrosion products and they become radioactive. So this sort of thing can happen.
So how do I know if I can come in the room or not? How do I know if it's safe for me to go in? Let's just hide in the safe area first. How do I know? Well, let's think about it.
Hey, the door acts as another layer of shielding.
So if we have different types of radiation coming off of these isotopes, then let's think about what we can do. We have alpha, beta, gamma, neutron. Well, we're not going to worry about neutron because that's mostly in the core of the reactor. So let's don't think about that right now.
Yeah, neutron's going to be indirect, and the main shielding from that is stay away from it. There's a physical barrier. At the plant I worked at was what's called the bioshield. That is to say, don't go in that thing while the reactor is operating.
So alpha stops at paper, beta stops at plastic, so we don't have to worry about them because they're contained in the steel pipe. But think about this gamma. This gamma could probably go through that steel pipe because you need something heavy like lead to stop it, right? So let's look at our little dog poop analogy.
So nuclear plant design is ALARA, as low as reasonably achievable. So having 8-inch lead surrounding each and every pipe, that's not exactly reasonable.
What could we do to prevent the smell? Oh, here's the thing we could do. We could put a little cover over the dog poop so the smell could no longer get to us. And since we know that lead stops gamma, we could do what we talked about earlier, right? We've got that lead blanket from the dentist office, you remember that? So is there a way we could wrap lead around this area of the pipe that has contamination in it to protect us in the room? And actually there is. You can just wrap that entire pipe with lead, and suddenly it prevents gamma from getting out into the room. And
you can wrap the pipe. You can also wrap the pipe and carry essentially lead shields with you if you're going to be working in kind of an area, or if, say, it was a different source where wrapping the pipe wouldn't work for whatever reason. There's ways to do it around your person versus the actual source. Either way can be effective depending on what it is you're doing.
Protects the person. So just like we were able to shield the dog poop to get over here, if we put lead over that radiation like that, then we can prevent the gamma from getting over here to where we are. So that's a really interesting technique.
It's a good concept.
That's the first way that a nuclear worker can protect themselves in a room with contamination. They can use shielding.
The other two are time and distance. He's starting with shielding, which is interesting.
Which is very interesting. They are now shielded from that radiation. Well, what's the other thing we do? All right, let's go back and look at our turd analogy here. So if I had to do some work around this dog poop and I got close, like the closer I get, the more uncomfortable I feel.
Okay, distance.
And you can see it with the nose even. Like if I come in close, oh man, it smells so bad, I gotta get away. If I change my distance, then I can keep myself safe. So I wouldn't want to do any work over here. I would want to work here if I can control that, right?
Yep.
So that's the second way that a
Double your distance from the source, the intensity drops by a factor of 4.
nuclear worker can protect themselves from radiation or contamination is keeping your distance from the source, okay? So we got shielding and distance. And what's the third thing we would do? If I had to work around that dog poop right there, man, it smells bad in this room. I would want to get out of the room as quickly as possible.
Yep.
So that's another thing we can do. We can just go over, do our work, and get out of there really fast. So yeah, that's fine. I'm gonna do it again. Get in there, get out, okay? That's called time. So shielding, distance, time. Those are the 3 tools that nuclear workers have to protect themselves from radiation. And this actually has
a great analogy.
A name. It's a program that's called, we want to keep our radiation exposure
ALARA.
as reasonably achievable, okay? And they call that, inside the plant, they call that the ALARA program. So basically, nuclear workers want to limit their exposure by applying shielding, keeping their distance, and limiting the amount of time that they are around any kind of nuclear source, which I think is really interesting. And if you think about it, that works with the way things work here. Man, I just want to get out of this room. But, oh no. Oh, okay. Oh, goodness.
We have a leak.
This is a big deal. So we no longer just have to think about the radiation. We now have contamination because that
highly possible if this suddenly happened while you were in there, your dosimeter would alarm, because this would be higher. Since it's outside of its shielding, you're going to be getting a higher dose than what you briefed, probably.
water was in that pipe where those radioactive particles were, and now it's dripped on the floor. So if we have to do any work in there, this could happen. We could walk over here, we could do our work, but on our way out, there's a very high likelihood that we might actually track that stuff out. And
this sort of thing were to happen while you were in there, odds are your job's going to get canceled because you would have to rebrief for a higher dose or something, and it would probably be rescheduled until after that thing is fixed. But let's see.
Because it was from that pipe with the particles in it, we could spread that contamination. This is a big deal, and we have to think about what to do here. We need to call somebody. So that's
notify the control room right away if you were to see something like that happen.
That's what happens in a nuclear plant. If there's a spill or anything like that, biggest of deals. You have to deal with it, and you have to deal with it in a very intelligent way. So you call these special people. They come out with special meters, and they check everything, and they have
Okay, he's referring to radiation protection. But yeah, call the control room, call radiation protection. Radiation protection would probably find out about this quickly anyway, but yep. So they can assess the dose before you would send people in to fix this leak.
Special equipment sometimes that they'll come and they'll clean everything up, and they'll make sure that everything's safe so that work can continue. One of the things that's very...
Okay, so if it was an inactive leak, HPs could probably clean it up, but you're probably going to want to get some mechanics that work on the valve itself if it's a leaky valve. Mechanics working with HPs to fix it. By the way, at nuclear power plants use the term health physicists and radiation protection almost interchangeably. They're a little different. Health physicists are more of the experts and radiation protections are more of the technicians, but at least where I worked, it was all the same department. So you would often see those terms used interchangeably, and people would still know what you're talking about.
Very important. The whole area of the nuclear plant has an inner area inside it that's called the radiologically controlled area. I think I referenced that earlier. This is a very special concept. It's like a section of the plant that's contained, and every individual source is located and quantified for its radiological effects.
Here's one other interesting thing. You have radiation detectors that are outside the radiologically controlled areas. Because you have a leak, you could have a boundary breach from your radiological controlled area boundary. It wouldn't be in this particular case. But then, guess what? The radiological controlled area boundary gets expanded, and then there are areas, say the turbine building, if you have, say, primary to secondary leakage in a reactor that leads to increased dose in the turbine building could turn into a radiological controlled area. Doesn't start out that way, though.
And so before you go into a plant, you have to check with the authorities, and they tell you, okay, if you're going to that area, there's a special valve over there that's hot, so you need to keep your distance or limit your time around it. This concept of the RCA is very, very important for ALARA because that's how they control where everything is. And so if there's a spill and it changes the area, they document all that in the RCA documentation, and you know where to go and what to do when you're there. So these are the main concepts that I learned in that training, and it was really good training, actually. There was a lot of numbers that went along with it. We got to learn how the core of the reactor worked, which I really enjoyed. But the last thing is
use neutrons to fission use neutrons, fission uranium, make heat. That's how the core works. That's it. And it's enough to make a chain react. That's it in a nutshell.
You have to take an exam. Now, I'm an engineer. I felt pretty confident about my ability to hang with all this stuff. You know, I think I get it.
Go for it.
George, however, theater major. A little concerned about George's ability to get all this right, so I was...
It's easy. There are people with zero college education background that take and pass these tests. Because some people, you just want highly specialized trades, like a highly specialized welder, for instance. Don't necessarily need a degree for that, but you need a highly specialized training, which they have, and you train them on radiological principles. And the nice thing is this is all at a very low level. You're not going to be asked to do any complicated math. The most complex math you would probably see on general employee training would be applying the inverse square law, and it would be as simple as someone has a dose of 1 millirem at 2 meters from the source, what would be their dose at 4 meters from the source? And the answer is 4.
A little nervous for George. Let's go see how he did.
Click on
What do you mean what I get? Don't even worry about it.
review your results.
I got a 92. What'd you get?
96.
Yeah!
Oh, I'm sure that wasn't staged, but gotta love it.
Oh, you beat me.
I got that one wrong too.
Hey, we got it.
In the nuclear industry, you say 8-0 and go, passing requirement's 80%. And you get a chance to review what you got wrong, and just to make sure you got it.
A warehouse on site that housed more hands-on training, and
Here
we
we
met
go.
Tim Lawson. Tim is what's called an RP instructor, radiation
Okay.
protection. I learned that RP professionals in nuclear plants are very important. They're like the watchdogs or the scouts that are constantly looking around the plant to keep the workforce safe from radiation. Tim briefed us on something called an RWP, or
Some plant operators that argue that they run the plant as far as inside everything that's inside the radiological controlled area. They really don't. It's all plant operations.
Radiological work permit. These are very, very important. Anything that happens in the plant, you first have to get an RWP, and you have to be given specific instructions about what you're going to do, what your radiation limits are while you're there. It's a very important guide that people use anytime they enter the RCA or
It's an agreement on how you're going to get the job done safely and minimize dose. This is what I see a radiological work permit is.
radiologically controlled area.
So here we have an RWP, and this will be the RWP we'll be using today going through out here. So it is all units, reactor building, general area activities. This RWP...
Let's see. So it's going to be low dose, general area. The first thing to look at is the color, and that's white. At the plant I worked at, it was white, yellow, and red. White's regular radiation area, yellow's high radiation area, and red is locked high radiation area. Keep those rooms locked because you don't want people to inadvertently scramble into one somehow, even though there's signs are clearly marked and you have to get briefed anyway.
has medium radiological risk, and the RWP set points are 80 millirem for the dose alarm and 80 millirem per hour for the dose rate alarm.
This
Set your
unit
dose.
that the RWP says millirem, I have no frame of reference for what that means at this point. And a little bit later, Tim explained like the scale of millirem. I'll just let you listen to that now.
This
You
should be
see
good.
negligible effects before 50,000 millirem, 50,000 millirem.
That's high. Negligible biological effects. Depending on some conservative cancer studies, the number I always see is 10,000 is where the risk is evident. As far as short term, though, that might be what he's getting at, because that high 50,000 millirem per year, you're gonna start to see drop in your white cell count.
The stations, the NRC's limit is 5,000 millirem, but then the station lowers that to the maximum of 2,000 millirem.
Yes, so the station is more conservative than the NRC, and same was place where I worked, but yes.
So your threshold for any biological effects is 50,000 millirem, and we are so far below that.
Have you ever seen
I'm a bit more conservative, and I'd call it 10,000. I think we're talking about two slightly different things. I'm talking about more of a probabilistic increase in cancer, and I think he's talking about loss of white cell count.
a fundraiser where the town will like put a big thermometer out in town square, and as people donate, it'll fill up the thermometer? Well, this is how I think about the dosage limits you're allowed working at a nuclear plant. So Tim just said that 50,000 millirem is what's required in order for biological effects to happen to your body, right? Now, in this
I feel more comfortable with the 10 number. Maybe I'm a bit more conservative than he is. Sure, for the case of this example, that's fine. Mild radiation sickness is 100,000.
case, that's way in the sky. That's off the board, okay? I'm looking at 2,000 millirem, which is what's allowable at Browns Ferry nuclear power plant. And this is how I think it works.
It's probably 200 for pregnant workers. The NRC limit is 500, and usually people kind of follow suit with giving it 1/10 of what you allow your regular non-pregnant workers, but that's due to the fetus being extra sensitive to radiation, as it mainly targets fast-dividing cells, and that's basically all they are.
So first of all, as a human on Earth, you are going to be exposed to radiation just as a function of being on Earth. Like
Background
that's
radiation.
Cosmic rays and stuff like that hitting you. You're going to get
And from the
radiation
ground.
just in the background of your everyday life. But because you are a nuclear worker that
It can vary widely, but we're still talking pretty low level.
works at a nuclear plant, and today
Few
you're
milligram
going to
a
get a radiological work permit, an RWP, and you're going to read it and you're going to say, oh, well, today I can get 80 millirem.
By the way, all these numbers that are typically given to you is above background. But for the purpose of the exercise he's doing, it's not going to matter.
And my dose rate alarm is 80 millirem. So what that means is I can go into the plant and I can do my work, and that's my limit. So let's say I went and I did my work and I got like 35 millirem, okay? Well, I would just add that to my little thermometer.
I've had long times in the plant for hours and gotten, I don't know, 2 or 3.
And tomorrow you do it and you got maybe 40. And so you do this over and over and over, and it's cumulative. The amount of radiation you're exposed to over the course of a year adds up. But
So based on that, you wear two types of dosimeter. The thing with the alarms, the DAD that he called it, is one of them. You also wear a different one that's a dosimeter of legal record that tracks this cumulative one over the course of a year. Usually have those changed out every 6 months or so.
let's say tomorrow you are required to go work in a different part of the plant that has a hot spot. There's more radiation there, and you might get more radiation than typical. Well, that's okay. As long as the RWP allows it, you're allowed to get that dosage of radiation. So this goes up, 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 and
But yeah, radiation protection guys keep track of this for every employee and every contractor.
they keep up with how much radiation each individual worker receives over the...
And if you're going from one plant to another, they basically take a snapshot of this. So you track it at all the nuclear power plants you worked at. Say you're a contractor that only works refueling outages. This sort of thing happens with them all the time.
course of their job. Now, there's two ways that nuclear workers can measure this. The first way is called a DAD, a digital alarming dosimeter.
I like the
now,
DAD.
a DAD is
I'm a
pretty
dad.
interesting. It works kind of like an old school pager that measures radiation. Now,
Nuclear power plants still use old school pagers, by the way. I remember getting one when I first started working, and this was in the early 2010s. So the fact that I was handed a pager, me, a millennial just out of college, I was like, what even is this? And do people still use them? Apparently they do. They also use fax machines.
I'm assuming it measures gamma. I don't really know, but it's pretty
It measures overall dose, alpha, gamma, beta.
interesting how it works because it's doing two things. It's measuring a rate, meaning on my RWP it says I can get 80 millirem per hour. So basically, the rate at which the thermometer is going up, that's what this measures. There's another thing you can use, and that's called the dosimeter of
Okay, that's what I was just talking about, the dosimeter of legal record.
legal record. Now, this one works a little differently. A dosimeter of legal record looks like this. It's like a little thing that you wear, kind of like a name tag looking thing. And this thing
That one you keep on you all the time, usually with your badge.
measures the cumulative effects of being exposed to radiation. So a DLR, basically how that works is you wear it for 3 months, and then after that, or some unit of time, you send it in to get measured, and they can look at it and they can say, oh, you got this much radiation in that time period. I'm assuming it's like some film in there, and they'll measure how much the film was exposed.
Basically, it's thermoluminescent. Basically, you heat it up, it tells you how much radiation you've absorbed.
Something like that. Not sure how it works. But these are the two tools that you can use to figure out how much radiation each worker is exposed to. So a DAD, a digital alarm
Milo.
dosimeter, that gives you the rate, and you can use math to figure out what the total dosage that you've received is. And a DLR, a dosimeter of legal record, that gives you just the totals over a certain period of time. All this is meant to give you an ALARA compliance, the as low as reasonably achievable goal. So these are not amounts of radiation you receive on that RWP. This is the upper limit. You don't
Yes.
want to go over these numbers.
There is a dose goal. The dose goal, every outage, every job, everything has a dose goal. This isn't a goal that you want to exceed. This is a goal you want to be well below.
And a really good radiation worker, somebody that works in a nuclear plant that's really good at their job, they will keep this number as low as possible, which I think is really interesting. Now, I understand all this, but what I don't have a feel for is, what do these numbers mean? Like 2,000 millirem, like how does that compare to other things? So I asked him, like, how does this compare to other professions, like radiation techs or people that are working in the medical field?
Astronauts get a significantly higher dose than people that work at nuclear power plants.
That are doing x-rays all day. How does this nuclear program for ALARA, how does that measure against other fields? And his response was pretty funny.
The medical field, that scares the hell out of me. What those people do with their isotopes is, man, they need the NRC on them. But they're not regulated by the NRC, we are. So both of my
Medical's regulations are different. You're also going to get dose. You're going to get a lot of dose working at a coal plant. They just don't monitor it.
sons work here. I feel like it is one of the, which is near and dear to me. I feel like it is absolutely safe enough to where my children can be here and have a very good career. And it's a good place to be. You're absolutely protected.
After we finished our classwork, it was time to head next door for hands-on training.
Here we go.
So the RP people in a nuclear plant, you're kind of like the mother may I. Like if I need to do something, I need to check to make sure that the area is safe.
Call the control room first, but yes, for anything that is in the radiological control area, you're going to want to get with these guys.
You guys have the equipment, you know how to clear an area, is that correct?
Yeah, that's correct. So what we'll do is we have a frequency of surveying every zone. So kind of like the Marines.
So I'm noticing he has BHI Energy on there. They're a pretty common contractor that you do for a lot of radiation protection type work. Though he looks like he's a TVA.
Go first every time. If it needs lighting in an area that's dark, you go in with a headlamp on and your meter, which tells you the radiation because you can't see it, smell it, or taste it. So we go in with our meters. We go in the dark, we monitor for conditions.
Please don't taste it. Don't have an engineer with a calibrated tongue or thinks they have a calibrated tongue attempt to do something like that.
When we have those conditions, we come out and we tell the person who's going to go in and hang the lights, hey, here's where the radiation's at, here's where the hazards are at, and here's where you are allowed to go, and here's where you need to avoid because these are dangers which are going to exceed your radiation work permit, exceeds the limits which we allow.
And so what you're about to do is you're about to test me on my ability to follow procedures, and I'm either going to pass or I'm going to fail, right?
That is correct.
Yeah.
Before we went into the mock-up of the radiologically controlled area, I had to learn how to
You failed people before, but it's usually just for not paying attention. It's the most common reason people fail these sort of things.
get checked in with a software system that tracks workers and their RWPs and the dosages as they enter and exit the RCA.
Yep.
I got my 2 mock-up dosimeters and reviewed our RWP.
Click yes, you've acknowledged that you have read and understand. And when you do this,
Dose alarm 40 millirem, and so that's how much.
This is one of those things that you need to be sure to read and the terms and conditions before you agree them, because it's going to tell you what your dose rate is and what your dose is.
I can be exposed.
no, that's how much you can receive.
That's how much I can receive. Thank you. And the maximum rate that this is going to alarm at is 80 millirem an hour.
Right, so if you walk into 80 millirem an hour, it's going to alarm while you're standing in the 80 millirem an hour.
Yeah. And no funny business like taking your dosimeter and handing it off to a buddy so you can get closer.
And as it accrues, 10 millirem, 15 millirem, 20 millirem, if it gets to 40, it's going to alarm, and it's not going to stop alarming, and you're going to have to exit and see RP.
Got it.
And to prevent that, we look at our dosimeter every 10 to 15
Man, I'm recognizing this binder here, this qual book with all the sign-offs for training and everything.
minutes while we're inside of a radiation area. And then that's going to activate the dosimeter,
Takes me back.
and it gives you your allowable set
receipt.
point. So right now, the station allows you 2 rem like we discussed, but it's only going to give you 40 millirem for this.
Yep. Difference between your per year limit versus, say, your per job limit.
Single entry. Even though you have nearly 2 rem, you can still only pick up 40 millirem for this single entry.
Tim then showed me how the turnstiles
Oh, the turnstiles. They're always fun.
work off of your dosimeter. And then I got dressed out according to the specifications laid out in the RWP with boots and gloves and a head covering.
So you're going into a contaminated area. Okay.
Tim talked me through the security door and the airlock procedures, and we headed into the mock-up area, and I was a little bit worried that I'd forget stuff from the RWP, but Tim reminded me that I have a little white trip ticket that the computer gave me when I logged in that had all the stuff listed out for me.
Your trip ticket.
The place I worked at it didn't look like a receipt. It was just a card on a piece of cardstock.
It tells you how much dose you can accumulate and how much dose you can walk into. So you have that on your trip ticket. So the only thing you have to really have in your head is what the conditions are inside of this contaminated area.
Yeah.
And
you can still take a map with you. So no, you don't need to rely on memorization with pretty much anything when working at a nuclear plant.
Discussed on the briefing. Here's a survey map here.
Yeah.
So we see
you can take a map
that
with
just
you.
inside the step-off pad is 2 millirem an hour here, and I don't reach across the boundary. It's 2 millirem an hour right there. It's 5 millirem right over here. It's 8 to 10 over by the high radiation area on one side.
This is all simulated because I saw it said for training use only.
It's 8 to 10 down that side of the high radiation area. Noticing the boundary is continuous. And it's a continuous boundary so that no one accidentally walks into an area while they're just looking up at something else.
Yeah, that is important.
Because a lot of people walk in a plant inspecting, so they have other things on their mind other than where the boundary's at. So that's a continuous boundary. So you're going in to check the following unit IDs. So I've got a list of IDs that you're going to look at. I would look at my dosimeter and make sure it was turned on before I went into the area.
Okay.
Still on, because we do have digital issues like the world does.
Okay, the dosimeter is on.
When I first walked into the mock-up, I was being tested, right? So I wasn't thinking about making a video, but after the fact, I realized this is interesting, and I asked if I could take
They probably wouldn't let you make a video of it anyway.
my camera back in there, and I filmed things from my perspective so you could see it. So I edited this
I
together
am surprised they let him do that.
so you
But I
could get
guess it's just a training area, so that might be okay.
an idea of what I was looking at while Tim was showing me things. So you'll get the idea, but I apologize for not filming this the best.
All right.
So you'll notice there's
I'm
not
impressed he was able to get anything at all, like they would just let him.
there's not a barrier here as we discussed, like the high radiation area, which is a yield sign, which is a caution. So there's no barrier here, and the only way in or out is across the step-off pad.
Okay, this gets interesting pretty fast. So this is the map of the area that I'm going to be operating in, right?
Okay, so it is radiological area and the radiation area and contaminated area, hence the protective clothing.
You can see we have a large contaminated area, or the radiation area, and up here in the corner we have a high radiation area. So what I'm supposed to do is as I enter right here is I go to the low dosage waiting area immediately. I misread this map, like right off the get-go.
You don't
and
wanna
I
do that.
immediately walked all the way across, and I thought this was the low dosage waiting area right over here by this pipe, and I just hung out there, which was the wrong thing to do. So yeah, that's how I started. I started
The low dose area should also have a green sign by it, too.
off wrong.
So you're looking for label number 1 is unit ID 2-PMP, which is for pump, 2-PMP-075-0020
It's over there on the left.
CS drain pump alpha.
So I'm just using my eyes. I'm seeing a pump over there. I'm not going there yet. I'm just trying to map out where I'm going because I want to be there for a minimum amount
This
of
takes me
time.
back.
Yes.
So I'm going to go over.
And you're just going to verify the ID.
Nope, that's the Radwater pump.
Hey, that wrench is not supposed to be there. Can you grab that wrench?
I will not grab that wrench.
That is very good. That's exactly.
Yeah. Try to trip you up with stuff like that.
Why wouldn't you?
Because that's the high radiation area and my RP won't let me.
Hey, would you straighten that hose if you don't mind?
That hose in the back there?
Oh, no.
Okay, I'm thinking I can't really get there without a stick or something.
Right, yeah. So you don't want to want to cross the
Just say no. No's never the wrong answer when it comes to stuff like that.
FME barrier.
Yeah.
And a stick in the FME barriers,
Yeah. So the FME barrier, that's a different sort of program than radiation protection. That's a program that you just don't want any foreign objects in exposed areas during system breaches, and that's mainly when you're doing maintenance on something. Of course, there are some areas, such as the spent fuel pool, that are always FME controlled areas. After all, there've been some severe accidents that have involved FME events.
Discussed is foreign material exclusion. So
Can't
we don't.
use a stick.
Well, you want to be you want to log and document everything that goes
Every
into
tool that passes the barrier.
Correct.
Okay.
Tim continued to ask me
I don't think that comes up later, though. That's its own specialized training, training you on good FME practices to be a good FME-ready worker, and you have all your tools tied up and everything like that.
to do different things and look at stuff in the environment. And these were basically ways to distract me. And so he would try to ask me to do something that would break radiation protocol, and he would see if I would catch it.
Correct
And
answer
so
is always
it
no.
was fun. When George and another TVA employee went through this exercise, I got to watch, and you'll notice that they're waiting in the correct low dosage waiting area. So there's that.
Yep.
This training helped us piece together a lot of the information in our heads into a simple set of behavior rules that would minimize our radiation exposure.
So shielding. So that shielding,
That's temporary shielding.
that is temporary shielding, and that is lead. So what if we had to do maintenance on that valve? Could you remove that lead shielding? If
I'm assuming if I
Look at what's in your maintenance procedure. It's a trick question.
got permission in my RWP, but
Your RWP is different from your actual maintenance procedure that's going to involve taking apart a valve.
it's not in my RWP.
it's not. So to remove lead shielding, RP would have to be present standing there, because as you remove that shielding, the dose rates are going to increase.
Okay, so you would have to monitor as I remove the shielding.
Correct. RP would have to be here, and would have to be as you remove it would be there. That's correct.
Yes, sir.
So
Tim had me follow the procedures for taking off my protective gear, which had to
Yes.
be done in a very specific way in order to minimize possible contamination.
Okay.
Yep. Now I'll note this: when you peeled it off, it came like out past the line here.
Don't do that.
If it had something on the
Maintain
bottom of it,
positive
it would
control
sling
of
it
your body
onto
on
the clean
exposed
area.
areas.
Wow.
And like I said, this is the most likely area to get a clean area contamination because of the migration of, like the dirt that will be on your shoes when it's sprung, it'll spring out into
So
the
I
clean
just
area.
rubber band shot a potential hazard that way.
So what I
Across the plane.
like to do is, and it's just a technique, is as I undress, I face inward.
Yeah.
And I pull everything off inward.
Oh.
And then like a doctor would back up to a door.
I finished taking off my protective gear and exited the radiation area, and then he had me scan myself for
the
possible
frisker.
contamination, which again was supposed to be done in a very specific way, which I remember from the written
1 to
test,
2 inches per second.
but struggled to do it in terms of a practical application.
Involves balancing yourself on one foot.
Then took me over and showed me how I would exit the RCA, which entailed having a full body
Yep.
scan done. And then, of course, I checked back out with my dosimeters with the software system. Obviously, I'd messed up the low dosage waiting area, but it was
Sometimes your pants could be contaminated and they make you take your pants off and give you temporary pants.
time for Tim to give me his final feedback.
I did have to coach you on the speed at which you were frisking.
Yes.
So that was one thing. So
Yeah.
I got you on the second attempt though, once I told you knew the speed. So but you didn't check your dosimeter while you were inside of the area.
Oh, that's
So you didn't look at it.
a big deal. Yeah.
Well, it's the first indicator that dose rates are not what you expect them to be. You did a perfect job on dress out. You used all the tools that were available to you. So, I mean, your dose is your bank account for your life, and you kept it ALARA.
So I was so distracted by the task,
Sure.
I didn't think about the radiation. I mean, I was thinking about it because of the map. I was seeing the map in my head, but I wasn't.
The jobs at nuclear power plant are probably 10 hours of briefing and 2 hours of wrench time, depending on what it is. Because it's not just about radiation protection. There's your FME brief, there's your plant status control brief to make sure you don't bump anything. It adds up.
Wasn't thinking about what I was actually receiving at the moment.
And that's a great point for why radiation protection concentrates solely on radiation protection.
Yep.
Just like security, when they're walking around the plant, they're looking for guilty people. They're looking for holes.
And FME monitors make sure all your FME devices are installed properly and you're following your FME procedures. Because there are stamps on your work documents that say FME device required or FME two-man closeout required.
In the system.
Yeah.
They're not thinking about radiation. Maintenance guys, they're looking for leaks and steam. And they're wondering, why is that line hot when it shouldn't be hot? That's their focus. Our focus is strictly radiation.
Well, yeah, that was a great real world scenario. I really appreciate the time. Thank you so much for teaching me.
Absolutely.
Glad you were able to
Good job.
show some
And
of it.
now, when I submit this paperwork, you will be fully qualified, okay?
Okay, we are now certified. We have moved from knowledge about nuclear plants to understanding. So we're about to go into the plant, and Bill's going to say a lot of things as he takes us in, but you now know what these terms mean.
cool.
So listen to what he says and see if you know what's going on.
All right, so here's what we're gonna do. We're gonna go in the RCA. You're gonna put your dad
Going in
on
the
here.
real
Philip will go in last. Just make sure you're all good. You get the green light, and we'll go in. Okay. Now you got your hard hat,
Yes,
safety
sir.
glasses,
Yes,
hearing
sir.
protection, DLR, and your dad, right?
Yes, sir.
Good to go.
Great.
It's a lot to keep track of when you first get started.
Currently, I have 0
That's good.
milliram.
Low dose waiting area.
Okay, so what I'm about to take you into is the secondary containment area, right? You'll notice that there's some locked doors and everything, like watertight doors. We do this intentionally because this is our absolute last means if something bad happened.
Yes, the containment structure is the outermost fission product boundary. The second one is the reactor coolant system, and the third one is the cladding around the uranium fuel itself.
Where we keep it all. We keep this area at a negative pressure just to make sure we keep all containment products inside secondary containment.
In contrast, you keep the control room at a positive pressure to keep contaminants out.
If something were to have happened. We're going to walk up to the elevator through the operating spaces because there's less traffic over this way.
And before we go any farther, when you see the floor drains, don't step on those.
Yep.
They're a lot of times contaminated. Okay? So be looking for floor drains.
The floor drains usually have little magenta tape around them. Yep, mostly what you see. Concrete, pipes, conduit.
Can you believe this? We're in a nuclear plant.
The part that's hard to believe is they were able to let you film some of it.
As a part of the Nuclear Power Deep Dive series, I am so incredibly excited. I'm going to show you something. It doesn't seem like it could be real. It's real. This is where we're going in the next video.
Where is it?
We're going to go over and over.
All right, so you're going to go there during a refueling outage above the refueling cavity. Are they going to let them ride the bridge?
Reactor core, as they refuel it, you're going to be right there on a bridge on top of this thing, and we're going to get
That's cool. You get to see the Cherenkov glow.
to look down into the reactor core. It is so incredibly fascinating. Now that we understand the radiation and how contamination works, you're going to understand what it's like to walk through the plant. And we're going to see like how that reactor works, and we're going to understand it. It's
Keep in mind, you can only do this when the reactor is shut down. Do not do this while it is operating. This was really fun to watch. Takes me back to initial training. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.